And that is the final point that we will see in the course, an experimental detail that we are measuring m over z, mass over charge instead of mass alone, and what does that spectra look like, and what is the real spectral analysis problem, and how and hopefully then with that defined you can see all the ideas we have seen so far, and then see how that can be also applied to solve the problem with the m over z spectra. Okay. And then we will also give some indications about the Beltway and the Turnpike problem. Like we said, the real world mass spectra, the kind of spectrum that you obtain out of a peptide is noisier than the spectrum 25 that we have seen. So, even though we are able to reconstruct tyrosine B1 from spectrum 25, real world data can be much more noisier than even 25% errors. Okay. And then also, like I said, it does not simply weigh the peptide, it gives you not m but m over z. And what do we mean by that? This mass m over charge z, the ratio, and then you look at some form of histogram of this m over z across all the fragments that are derived from the peptide. Okay. And the height of the bar is going to be your intensity or the abundance of the ions that have a certain mass over charge ratio. Okay. And how does it look like? It looks like this. On the x axis here is m over z, and the y axis here is the intensity. And so, you have here particularly this 1300, around 1300 you have a very high intensity peak, and then that has this particular m over z. So, there are many fragments that have this m over z value of close to 1300, and then there is one more peak here, another peak here, and so on. So, these are all the peaks, and different peptides will give you the different profiles of peaks. So, this diagram will look different for different proteins, for different peptides. And so, the idea is then to, given this kind of a diagram, then how would you figure out what is the sequence that gave you these peaks. Similar to a spectrum of masses, now we have a spectrum of mass over charge. So, maybe some of the ideas that we have seen already could be tried here, and then more advanced techniques could also be applied. So, the challenge is reconstruct a peptide from real spectrum. And what are some of the computational problems? Okay. So, we have seen this experimental detail, and this experimentally what kind of spectra you obtain, and then how do you then look at other computational problems that may be helpful to solve this spectrum to peptide sequencing, right. So, this sequence reconstruction problem. So, there are two problems mathematically, they are well defined. You have a collection of points along a circle, and you have all the pairwise distances between the points. Now, you want to figure out what the arrangement of points are on the circle given just the pairwise distances. Okay. So, this is very similar to the cyclopeptide sequencing problem, right. So, you have 4 points here on the circle, and then you look at all pairs of distances along the circle. Okay. This is one distance along the circle, this is another distance, this is another distance, and so on, right. You look at all these pairwise distances. Here the neighboring distances are 2, 3, 5 and 3, right, but all these pairwise distances between these two green points it is 2, between these 2 points it is 3, between these 2 3, 5. So, these are these neighboring points distances. Now, you have another 5 from this to this, you have 3 plus 2 5, right, this to this you have another 5, you have 8 and so on, right. So, you can just look at distances between all pairs of points in both directions, clockwise direction and also anti-clockwise direction. Going from the arrangement of points on a circle to the pairwise distances along the circle, where the distance is measured along the circles, is an easy one, right. But of course, what we have is pairwise distances between points on a circle, and we need to figure out where the 4 points are placed on the circle. Okay. This is a hard problem, right. In fact, there are versions in the exact version of the problem, it's not even known whether it is NP hard or not, but there are certain noisier versions of the problem where NP hardness had been proved. And so, there is not much known about this Beltway problem, where you are trying to figure out where the cities are on a circular road given pairwise distances between the cities. Okay. And this is very closely related to the cyclopeptide sequencing problem. If you do not have a circular peptide, you have a linear peptide, right. And then you are asking, in this case it is a turnpike is a linear road which is not a circular road, right. Then you want to place cities on there, so that it realizes the pairwise distances between the cities. So, here for instance, you are given 1, 4, 8, 9, 12 and 13, these are the pairwise distances between 4 cities, right, on a linear road, and then I want to construct what the actual locations of these cities are. Interestingly, the turnpike problem, again we do not know of any efficient algorithms, but then it admits a pseudo polynomial time algorithm. meaning that it returns an algorithm that is polynomial in the maximum length between any two cities, okay, the length of this line segment, but it is not polynomial in the input size expressed in terms of bits, right. What it means is that if you have the maximum length is 25, right, what it means in practice is that if you have the maximum length is some small number like 25, it will run in polynomial time in 25, but then if the maximum distance between cities is 10 to the power 50, it will run in polynomial time in 10 to the power 50, not in 50. Okay. So, so that is what a pseudo polynomial time algorithm means. So, this means that the Turnpike problem is a bit easier in some than the Beltway problem in the sense of practical ease, right. We know of a pseudo polynomial time algorithm to solve the Turnpike problem, but there is an open problem on how to it is an open question on whether we can have any similar algorithms for the Beltway problem. Okay. And then the pseudo polynomial time algorithms can work for input instances where the difference between the maximum distance, pairwise distance between the cities is not too large, like in this case. In this case, it will again be too slow. So, this is again an open question on whether we can find a pseudo polynomial time algorithm for the Beltway problem. An algorithm for that will directly translate to an algorithm for the cyclopeptide sequencing. We have seen that we have used branch and bound techniques and other heuristics to solve that problem, but if we can get a pseudo polynomial time algorithm, then we will have a provably efficient algorithm, at least in the pseudo polynomial sense, to solve the problem. Okay. With these comments on open problems in cyclopeptide sequencing, which is the Beltway problem, and then in Turnpike sequencing, which is the linear peptide sequencing problem, where again an open question is, can you do better than pseudo polynomial time, right. With these open problems, I will just conclude the session saying that again whatever we know in terms of these problems in bioinformatics, we are at the tip of the iceberg, and then many more interesting things are waiting to be solved by the next generation of bioinformaticians. Okay. I will just stop here. Thank you for your attention and time.